Recall that S3 is the set of all permutations of the numbers 1, 2, and 3. Let's do a calculation using an example. So it's sigma and tau. Those are elements of S3 as shown below. Let's compute their composition, sigma composed with tau. So remember that tau here is the inside function, and so it gets applied to the numbers 1, 2, and 3 first. And so tau would send 1 to 2, and then sigma would send 2 back to 1. So the net result of the composition is that the composition sends 1 to 1. How about the input 2 here? Well, tau gets applied to it first, and tau sends 2 to 3. But then sigma sends 3 back to 2, so the net result is 2. Now we know that this product is also a permutation, so it should be the case that 3 gets sent to 3, but let's verify that. So tau sends 3 to 1, and then sigma sends 1 back to 3. And so we see that their composition sends 1 to 1, 2 to 2, 3 to 3. It's the do-nothing composition, which we called epsilon. So let's do some review here. Epsilon is the identity element, the identity permutation. And we just saw this relationship that sigma composed with tau is equal to epsilon. And I'll leave it up to you to compute that tau composed with sigma, if you just swap those two in the composition, that also equals epsilon. And therefore, we say that sigma and tau are inverses of each other. In other words, tau is the inverse of sigma. That's what this expression says. And we can also say that sigma is equal to the inverse of tau. And that's what that expression says right there. And so I'll ask you to pause the video right now and see if you can recall what it means to say that S3 is a group under composition. What group properties are satisfied by S3? And so please pause the video for the moment and see if you can come up with the group properties that are satisfied by S3. Here's the long-awaited definition. We say that the set S3 is a group under composition because it satisfies the following 4 group properties. Here they are. First, closure. S3 is closed under composition. In other words, if sigma and tau are 2 elements of S3, then sigma composed with tau is also an element of S3. Second is associativity. The operation of composition is associative, meaning we can regroup or move parentheses around when multiplying or composing 3 or more elements. Notice here that the order in which these 3 elements are listed, sigma, tau, mu, that's the same on both sides of this equality. It's just that we can move parentheses around or regroup them in any way that we like without changing the outcome. Third, S3 contains an identity element, epsilon, such that epsilon composed with alpha is equal to alpha, and alpha composed with epsilon is still alpha for all alpha in S3. So such an identity element acts like the number 1 if you were multiplying, or the number 0 if you are adding. And fourth, but not certainly not least, each element sigma in S3 has an inverse element that's also in S3, And typically we denote it as sigma inverse, such that when we compose them together in either order, so sigma composed with sigma inverse or sigma inverse composed with sigma, both of those would equal epsilon. And so each element has an inverse. That's also in S3. And so those are the four group properties, and a set and an operation that satisfy those four group properties is called a group. Now here's a couple of words about the convention that we'll use. First, with most groups, we'll employ what's called the multiplicative notation. And so we'll treat as if these operations are just multiplication. And I know with permutations, I've often said the product instead of a composition because I'm used to thinking of them in terms of that multiplicative notation. And so for instance, in S3, instead of writing sigma composed with tau, we can and often do write sigma tau, treating it like a product, the operation being multiplication. The only exception to that is when we know that the operation is addition. So for example, the group of integers, which is a group under addition, if we know that the operation is addition, then it would be natural to use the additive notation. And so we would write, for instance, 5 plus 2 equal to 7. And so that's the only exception. Typically, we would use the multiplicative notation. If we're talking about a general group, we would assume that the operation is multiplication, unless we specifically say that it's addition. At this point, please pause the video and work on Day 8 classwork. Afterwards, we'll review some of the problems and concepts. Let's start by looking at some examples of groups under addition. Now these include the set of integers z, that's a group under addition, or z10, or z7. Since we have the z10 clock right here, let's look into z10. In z10, we see that 3 plus 7 is equal to 0. And that relationship tells us that 3 and 7 are additive inverses of each other. Now, more specifically, we can say that the additive inverse of 3 is equal to 7. And symbolically, we can write the additive inverse of 3 is equal to 7. So that's what this equation is telling us. Now, I'd just like to highlight that this is very much consistent with the Z10 clock calculation that we've done before. Recall that when we think about -3, we would often write that as 0 minus 3. And in order to compute 0 minus 3 using the Z10 clock, we would start at 0 and then go counterclockwise 3 units. So 1, 2, and 3, and notice that we land at 7. So our old way about thinking about -3 is consistent with this new notation of, or new interpretation of -3, namely the additive inverse of 3, which is equal to 7. Now, I like to highlight something a bit more general from this example, namely, when the operation is addition, we talk about inverse elements. They're additive inverses. And we would denote additive inverses using the minus sign, -x, rather than x to the -1. This refers to the multiplicative inverse, and that's when the operation is multiplication. And so when the operation is specifically addition, we would use -x to denote the additive inverse, rather than talking about x to the minus 1, because this notation again is reserved for situations where the operation is multiplication. Now, speaking of multiplication, how about these groups? Z, Z10, Z7. We know those are groups under addition. In problem 2, we asked, are Z, Z10, and Z7 also groups under multiplication as well? Because we can certainly multiply in Z, Z10, and Z7. However, those are not groups under multiplication because in each case, there is an element that doesn't have a multiplicative inverse, namely the 0 element. There is no element x such that 0 times x is equal to 1. That cannot happen, and therefore 0 does not have a multiplicative inverse in Z, Z10, or Z7, and hence those are not groups under multiplication. They're just groups under addition only. In problem 4, we saw that in any group, we have the following relationship, which we think of as the multiplicative inverse of AB is equal to the multiplicative inverse of B times the multiplicative inverse of A in that order. And so let's see why this is true. We'll give a couple of explanations for it. First is the algebraic explanation. So let's do some calculation. If we multiply AB by B inverse A inverse, let's see what we get. Well, we can use the associative property to regroup, move parentheses around, and so we can isolate those middle terms, and that's B times B inverse, and that becomes epsilon. Of course, epsilon is do nothing element, and so this is really just A times A inverse, and that also equals epsilon. And so we just saw that AB multiplied by B inverse A inverse is equal to epsilon. And I'll leave it up to you to verify that the other way around is also true. In other words, B inverse A inverse times AB is equal to epsilon. And so what we see here is that AB and B inverse A inverse, those two elements, those two products, if you will, are inverses of each other. In other words, the inverse of AB is equal to B inverse A inverse. If we translate this into symbolic form, it turns into the inverse of AB is equal to B inverse A inverse. And so that's how we justify the expression right here. Now, a little more conceptual explanation, if you will, is what we call the socks, shoes explanation. So think of A as the act of putting on socks, and then think of B as the act of putting on shoes. We're trying to compute AB inverse. So that means we are undoing the product AB. So if we put on socks first and put on shoes second, and you want to undo that process, so the product, what has to come off first? Well, the shoes have to come off first, and that's why undoing AB is the same as taking off shoes first, followed by socks. And so that's what we call the socks, shoes explanation of that relationship. And so this relationship here is true in any group. And I like to end this slide with one more remark, namely, if we have a commutative group where the order in which we multiply these elements doesn't matter, then we still have AB inverses B inverse A inverse. That's always true. But because we have a commutative group, B inverse A inverse, those can be flipped around and say that's equal to A inverse B inverse. And so in a commutative setting only, we can say that AB inverse is equal to A inverse B inverse, which looks familiar to the exponent law that we might have seen in the past. But again, this only holds in the commutative setting and not in general. Let's talk about problem 5a, which had to do with the interpretation of an expression such as sigma to the minus 5. So there are a couple of possibilities here. We can think of sigma to the minus 5, as Elizabeth did, as the inverse of sigma raised to the 5th power. Or as Anita did, sigma to the 5th power, and then invert that. So who's right? Well, it turns out, perhaps not surprisingly, that those two expressions are equivalent. And so let's see how we can show that. Well, let's start with Anita's expression. So sigma to the 5th, the inverse of that. So sigma to the 5th means sigma times sigma times sigma times sigma times sigma, and we like to invert that. Well, let's do a generalized version of socks shoes. Imagine this red sigma being socks number 1. And then on top of that, you wear the blue socks. And then the golden socks on top of that. And then the green socks. And then perhaps after that, you put on the orange shoes. Now, if you want to undo all of that, meaning take the inverse, well, what comes off first? Well, I guess the orange shoes. And then the green socks, the gold socks, the blue socks, and the red socks. Those come off. This is our sock shoes. It's just we have many more socks, perhaps. But then this product is just sigma inverse multiplied by itself 5 times. A shorthand for that is sigma inverse to the 5th power. And therefore, Anita's expression and Elizabeth's expression are the same. So which one do you use? Well, it depends on the context, and we'll see scenarios in the future where both interpretations could be useful. We're going to prove a theorem that's often called left cancellation. In other words, if AB equals AC, then we can cancel A on the left and end up with B equal to C. There's the analogous right cancellation, and I'll ask you to read about that in the textbook. But let's think about the proof of left cancellation for now. And so we'll do some scrap work first. I'll write the hypothesis on the very top. This is our starting point. And then we like to end up with B equal to C. Now, I like this particular proof, not because it's some monumental result, but because it utilizes many of the group properties that we have. And so, well, what do we have here? A, B equal to AC. Well, we want to get rid of that A. Well, what gets rid of A? Well, the multiplicative inverse of A. And so we would multiply by A inverse, and so there's the inverse element already, and we'd multiply on the left of each side of our equation. And so our original equation was AB equal to AC, and we multiplied both sides on the left by A inverse. And now we can use the associative law to regroup, because we want to isolate A inverse and A so they cancel each other out. And then A inverse times A is the identity element. So now the identity element shows up, and then certainly the identity element doesn't change anything, so epsilon times B is B, epsilon times C is just C. And so that is our scrap work, our proof outline, if we will. And so let's use that to write down our complete proof. And so as usual, I would underline the hypothesis and the conclusion. That gives us the very first and last lines of the proof. And so we'll assume, let's get the pen here, assume AB equals AC, and then at the bottom, thus B equals C. And so let's proceed as we did in the scrap work. We'll left multiply by A inverse to obtain, and notice here we're using the multiplicative notation. That's typically what we do as a default when we're talking about a general group. So we left multiply by A inverse to obtain the following. A inverse times AB is equal to A inverse times AC. And so once again, this was our original equation, AB equal to AC. That's what we see here. And we multiplied on the left on the both sides by A inverse. And then by associativity, we get to move the parentheses around. So I can write it here. A inverse A times B equals A inverse A times C. But A inverse A equals the identity because A inverse and A are inverses of each other. And thus, we have it right underneath. Epsilon B equals epsilon C. And so that's what we have. And since epsilon is the identity, and since epsilon is the identity, we have, let's see, we might have to move this last line a little bit here at the very end. We have that, I just want to say that epsilon B equals B and epsilon C equal to C, because epsilon is the identity element. So since epsilon is the identity, we have epsilon times B is just B, and epsilon times C is equal to C. And thus, this equation here becomes B equals to C, and that's what we wanted to prove. And so that's the end of this proof, and also the end of this lesson. So I will see you next time.